I'm Pascal. I'm sharing the first session, and I think to keep on the schedule, we directly start with Rhys' talk. He's from Radical and I, and will tell us something about closed loop. So the stage is yours.
Hello. So it's a great pleasure to be invited to speak, both as an early career researcher and a sort of representative of the sort of industrial space. It's also a great pleasure to speak to the first audience that might understand the relevance between radical species and material science. There we go. Okay, so what we're working on at Radical AI is to build a company that discovers and commercializes materials. And the sort of platform that we're building is this conventional materials flywheel. So sort of the optimize, automate, get the feedback, predict, and cycle this loop in order to accelerate discovery. The system that we're building is called System 1. And this is sort of preliminary, what is the minimal viable system we can build that shows that we can actually accelerate a commercially relevant materials discovery program. And so when we say commercially relevant materials discovery program, what we mean is we want to avoid the temptation of easy optimization. So at the moment, lots of people are automating experiments that we were already good at running in high throughput. So sort of liquid handling experiments, sort of powder dosing experiments, mixtures experiments. And we want to try and automate experiments in areas that were seen as true bottlenecks to sort of material science R&D. So our sort of scientific co-founder, Gerben Cedar, is famous for his A-Lab project at Berkeley, which was one of the first labs to automate sort of ceramics production. And sort of the sort of interesting things about the way that they achieved that was that it is in many ways incredibly wasteful. So when they powder, when they ball mill things, they have a lot of consumables. When they use pestle and mortars, they have a lot of consumables. And so one of the things to consider about automation is that for automation to be valuable in pushing the field forward, we have to sort of dramatically reduce the cost of experimentation. So whilst early sort of academic demonstrations can get away with running sort of through large numbers of consumables, sort of using disposable pestle and mortars, as we move to sort of an industrial scale, we need to make sure that we're both sort of massively driving down the cost of experiment and sort of solving a problem that otherwise was sort of prohibitively slow. So the problem that we're starting on is structural metal, so alloy development. I think it was a day or two ago, somebody showed a slide which had sort of where trends in material science heading, and sort of since the sort of 2000s, the amount or the proportion, or not 2000s, the 60s, the proportion of material science research dedicated to alloy development has shrunk dramatically. There was a sort of slight resurgence in the early 2000s that I'll touch on, but in general, the cost of developing new alloys is prohibitive. An example of this is that there was this MAC program funded by DARPA, which was $20 million for 500 experiments. And of those 500 experiments, I think GE Aerospace filed something on the order of 50 to 100 patents. So this is extremely sort of lucrative, but the sort of way that we do experiments is so prohibitively difficult in the alloy space that we don't sort of have success. So sort of these are three paradigms that sort of are used to explore in the materials space. So sort of arc melt reacting is sort of essentially this lightning in the bottle scenario. You have an evacuated chamber, you flood it with argon, you have a sort of tungsten electrode, and you sort of heat these metals up to sort of 3,000–4,000 degrees with a plasma, sort of limited to small scales, incredibly hard to automate because it's a sort of artisanal process where the person driving the experiment has to sort of react in real time to the mixing of the alloy, allow it to cool, flip it in order to get good mixing. Sort of as we move along, sort of induction furnace alloying is a great technique. It's much more easy to automate because you have eddy currents that do the mixing itself. But the sort of limitations of induction furnace melting is that because you have a crucible, a ceramic crucible, you're both limited by reactions between your ceramic and your metal, and you cannot sort of go outside the sort of thermal limits of your ceramic. And then sort of at the bottom end, we have thin film sputtering. So this is this sort of easy to automate experiment. So sort of lots of high throughput or combinatorial studies in alloys have used sputtering experiments because you can cover a huge compositional space, you can get a lot of great insight, but the sort of challenge is that unless you're interested in coatings exclusively, the thing that you are making is not industrially relevant. So at Radical, we're working on arc melt reacting and automating arc melt reacting. So the first test case that we're looking at is bulk metallic glasses. So if you look at this Ashby plot of yield strength against fracture toughness, you see that bulk metallic glasses sit in this top quadrant where they have exceptional yield strength and sort of very high fracture toughness compared to conventional ceramics. So Taylor is in the audience. I will not try to explain everything about why bulk metallic glasses are interesting, but our sort of VP of System 1, a professor at Yale, Jan Schroers, did a great podcast with Taylor where he'll explain some of this. But sort of broadly, a metallic glass is made when on this TTT sort of time temperature transformation diagram, you cool at a critical rate such that you pass this sort of nominal viscosity of 10 to the 13 before you have had a chance to nucleate any phase. And then you get lots of exceptional properties from the fact that you do not have a crystal structure. So often in alloys, the properties are dominated by the microstructure, which doesn't exist because you have a fully amorphous phase, and the sort of the presence of grain boundaries, the presence of dislocations, all these sorts of things. So sort of you get various properties for free. So because you have a disordered structure, your radiation resistance is good because you get knocked out of sort of a pseudo-equilibrium position and then you relax back. Like the difference between an irradiated structure that is damaged and a normal structure is much more minimal. So you can sort of rely on them in engineering scenarios. Corrosion resistance is an interesting one because sort of in lots of alloys, principally your corrosion will start at grain boundaries. And so if you have a system with no grain boundaries, then you have no place for sort of corrosive species to attack. This exceptional elastic limit is because you don't have dislocations, dislocations are what allow sort of the deformation of metals to occur easily. You can deform these materials to a large extent, and they'll spring back exactly to their initial shape. So this is sort of very interesting for various applications in robotics, like living hinges being sort of on your water bottle now, where you have a hinge that flips up. It's a continuous piece of material that operates as a hinge. The other thing that is really, really exciting about bulk metallic glasses as an application is this ability to do thermoplastic forming. So with a glass, what you can do, or you have sort of two key temperatures. So you have a sort of glass transition temperature where your material starts to soften, and then you have this recrystallization temperature where you might start to nucleate new phases. And so if you can design a material that suppresses the recrystallization temperature, then you can cast a glass, heat the glass up to the point where it is sort of processable with sort of thermoplastic methods developed for conventional plastics, and make incredibly intricate sort of pieces of equipment with or parts with bulk metallic glass. So sort of one of the sort of principal sort of examples that you might give of a sort of next gen application that is only possible if we can develop superior bulk metallic glasses is there is a NASA program at JPL led by I've forgotten his first name, but Professor Hoffman, who is working on gears made out of bulk metallic glass. So these gears are exceptionally interesting because of being ceramic, they have very high wear performance, which means you can use them in a lubricant-free gearbox. But you cannot use, but the sort of key engineering limitation they have is that, let me take some steps back. So on the Curiosity rover, 40 to 30% of their total allowed power that they collect is used to heat the lubricant in the gearbox, in this like warm box. So if you can remove the need to heat the gearbox, then you have a sort of, you can either reduce your battery, reduce your solar cell by 40%, sending things up into space, sending things to Mars is exceptionally expensive. So if we can replace the gears in the gearbox, then we have a huge sort of additional budget to do more science, more sensors, more things like this. And so what a gear would need to withstand is it needs to withstand crash landing on an alien planet, and then be able to be used in a lubricant-free gearbox. So this is a sort of application that is one of these things that metallic glass is the only solution to. And one of the reasons that metallic glass is really interesting to us at Radical is metallic glasses can only be considered in their as cast microstructure. So one of the things that is exceptionally challenging about alloy development is often we will make an alloy, we will then sort of work harden it or sort of cold work it to put in a whole bunch of dislocations energy. We'll then heat it up, heat treat it to equiax the grains. So the sort of thing that you make is very different from the properties you get at the end. Whereas with bulk metallic glass, because you can only achieve it by cooling very quickly, you can only use the equilibrium microstructure, not the equilibrium microstructure, the as-cast microstructure. So in terms of an early application, it actually means that we can start working and getting results without needing to build out this entire sort of heat treatment facility. But when we have built out the heat treatment facility, the sort of next step is to move into this multiple principal element alloy space. So the bulk metallic glasses we consider are an example of multiple principal element alloys as opposed to sort of conventional dilute alloys. So sort of alloys like steel are sort of 95% iron with sort of some dopants and substitutions, whereas these sort of multi-principal element alloys is a sort of field that exploded at the sort of start of the 21st century, where you had sort of simultaneous research from the Cantor group at Oxford and another group in Japan showing that actually you can mix alloys that sort of conventionally defy expectation. So you can get single-phase systems with many, many different principal alloys. And so what this actually opens up is it opens up this huge sort of combinatorial search space where we have these sort of cocktail effects where you mix together things that you wouldn't conventionally mix together, and you can get very interesting and critically tunable properties. And this is exactly the type of space that is well suited in the limit to sort of high throughput data-driven experiments. So this is the sort of crux of where we're going with alloys. This is a sort of a brief slide sort of saying what's so challenging about alloys. So these are sort of 3 SEM micrographs from one single sample cast in this wedge shape. And what we see is that at the tip, we have a sort of beautiful glassy structure. In the middle, we have these like spherulite growing nucleating grains. And then at the bottom, we have this sort of weird needle-like lamella structure. And this is the same material. And so the question is sort of, there are an inordinate way, a number of ways in which an experiment we can run will fail because we didn't see the correct microstructure to know that what we had discovered was actually the needle in the haystack. So the question is, how can we design a process that lets us see these? And sadly, I am not allowed to share any more about our lab today than what I've said so far. So what I'm going to shift to for the rest of the talk is I'm going to talk to you about the work that is being done by our simulation teams. So broadly, we have sort of two team setups. We have this sort of mechanical engineering and software engineering team working on this orchestrated lab. And we have this computational design and AI modeling team, which I sit in, sort of working on what can we run in the lab. So sort of here, everything that's been alluded to this week in terms of computational workflows, we are also mimicking. So we are running DFT in order to collect sort of data specifically about BMGs and sort of high entropy alloy systems. And then we are funneling this data into various workflows in order to try and determine properties or descriptors that might then steer our study. So sort of one of the things that we're doing is we're studying these sort of gamma surfaces, as they're called, which are the surfaces you get if you deform, is you sort of slice the unit cell and then deform it. And what this allows you to do is to look at stacking fault energies and other energies in the alloy structures. And then these can be sort of correlated to things like dislocation motion, which can then be correlated to things like sort of yield strengths, hardness, etc. And the sort of correlated aspect is interesting to us because what we can do is we can use these things as descriptors. We don't have to rely on them being sort of quantitatively predictive because we are feeding them into a wider machine learning framework. The other things that we're doing are we are taking sort of conventional sort of bulk property assessments and extending them both to this sort of quasi-harmonic approximation and the aharmonic approximation and looking at the temperature dependence of things through simulation rather than just the sort of 0 Kelvin bulk modulus, for example. And then this brings us to ML within our sort of material space. So this is actually a real-time graphic of the speed of DFT against the MLIP. It is about 1,000 times slower, which is critical because sort of these sort of quasi-harmonic and aharmonic approximations require sort of thousands of times more evaluations than sort of the sort of harmonic approximations. And so the question is, in a space of alloys where there is limited alloy DFT data, or at least limited sort of large-scale alloy DFT data, because sort of these alloys that we're studying are both disordered, which means that you need to sample many, many quasi-random structures in order to get a good understanding of the alloy. And in general, they have many, many more valence electrons that you need to consider because of the position of the elements in the D block. We have a sort of a problem with knowing which is the best model to use. And then there's also this problem that as soon as you define a metric in this MLIP space, people start optimizing towards it, which brings me on to MapBench Discovery. So MapBench Discovery is a long-running project between János Rybsel, who is also a colleague at Radical AI, and myself, which was sort of our contribution to trying to both show that these MLIP models had reached maturity in some regards and benchmark them in a way that sort of was less susceptible to being gamed. And I will sort of talk about how we now believe that this is increasingly saturated and where we should go next. So sort of the sort of principles behind the development of MapBench Discovery was actually, I was interested in benchmarking a model that is now so bad that it doesn't even appear on this first page of 19 models against MegNet, which is the third from the bottom. And the way that people were comparing before is often people would develop their own benchmark suite that they used within their internal group. They would then have to run everybody else's models. You're not necessarily going to put the same amount of effort into tuning somebody else's model as you would your own. And then you have these sort of benchmarks that sort of mostly give a coherent sense of which models are better, but you couldn't necessarily trust them. So our aim was to sort of try and create a benchmark that was in some sense fair, and in some sense targeted at a real use application. There's a question, but I think we'll leave them till the end. The first task that MapBench Discovery consisted on was this task where we took data that was kindly sent to us by Haichang Wang, who is one of Sylvia's collaborators, for the initial structures of one of their screening campaigns. And we said, if you only had the initial structure and the data that was available in the materials project, how much could you accelerate the campaign that they ran? So that's this direct acceleration factor number. And initially, we were getting sort of accelerations of 3x, and now we're at accelerations of 6x because we're sort of nearly saturated the benchmark. So if you dig into the page, you can see sort of more additional plotting. And you can see sort of in the top plots here, we plot the precision and recall as a function of the experiments requested by the model to be made. And you can see that for models trained exclusively on materials project data, we now have a very tightly grouped bunch of models that are essentially the same. And for models that are trained on MP-Traj plus Alexandria plus the OMAT data, you have again the same thing. So we're sort of at the point where I think conclusively the benchmark has shown that the thing that matters more so than architecture, at least in terms of these metrics, is data. And you can see this in this bottom right plot, which shows that the models, for the most part, are entirely in agreement about which things in the data might be wrong and the things that the data is insufficient to fit. So the bottom, you have this sort of lighter cluster, which is everything where the models have sort of an error, but the error is sort of consistent amongst all the models. And then the things where there is a much higher error, then this is, you have sort of an inconsistent error between all the models. So this is broadly things where the model is unsupported by its training data, and so all the models are different, and things where all the models feel supported by the training data, but are wrong with respect to the DFT calculation. And this can either be that the DFT calculation is sort of misspecified or misconverged, or there is sort of some fundamental limitation of the locality assumption of the MLIP models. So now that we've sort of broadly seen that this first task is saturated, in order to try and keep understanding which models are better, we've been sort of scouring for tasks that we can add. So the sort of first task we added was sort of driven by this assumption, or driven by this sort of interest in, do the MLIPs sort of preserve the symmetry that we see? So these sort of initial large-scale models that sort of really did ramp up the performance on the benchmark, but sort of by taking these sort of machine learning first solutions, so for example, Equiformer V2, if you look at whether the symmetries are preserved in the structures, you would see that Equiformer V2, despite supposedly being equivariant, destroys all symmetry, knocks everything off its symmetry sites when you sort of consider a sort of fairly routine symmetry precision. And so this is like a really interesting insight because it actually shows that sort of trying to build the model that preserves physics is more important than the metrics that these models were being sort of optimized for. And we've seen in a later iteration, they've come back with a sort of gradient-based model, and this preserves the symmetry much, much, much better than the original sort of direct force prediction model. The sort of next aspect that, that has been contributed to the benchmark is this sort of idea of we're only training on energies and forces. Are the MLOPs sort of able to capture this sort of higher order precision? So if we look at the sort of potential energy surface as an expansion, we see sort of the energy and forces terms are well studied, but these sort of Hessian second order and even in the future third order terms, there are no sort of, or there were no effective benchmarks. So sort of, as Carsten talked about yesterday, what we actually care about is observables much more than sort of do we get correct energies. So one sort of observable of interest is this total thermal conductivity that can be calculated. But what our collaborators, Michele Scimurotti and his students, Michele Simoncelli and his students showed is that actually, if you use the MLIPs to study this sort of macroscopic quantity, what you see is sort of error cancellation. And if you study the individual phonon modes, which is shown in the sort of middle figure, you can do really, really badly at the individual phonon modes whilst being quite good at the overall thermal conductivity. So they proposed this kappa symmetric relative mean error metric that sort of exposes the fact that you don't just want to be good at the observable, you want to be good at the observable for the right reason. And if we go back to the benchmark, again, you can see that this equiformer V2, orb V2, did really, really badly at this task initially because it wasn't a consideration of people who do not have a physics background to develop the models for these purposes. And as soon as we add the task, suddenly it becomes a sort of signal that these people can optimize towards. And we've seen both Meta and the Orb team return with models that are much, much better at this kappa-SRME table. So again, it is the point that sort of data leads the model. If you have the correct data to assess the thing that you're interested in, people will produce models that will be useful for you to use. Sort of one sort of thing to say about the benchmark is in this way that we're saying sort of it saturates and improves, we sort of want to make the visualization and the sort of stuff as sort of interactive as possible. So we've recently moved to this combined performance score, which allows us to sort of re-rank different metrics. It's a really nice interface. I'd encourage you to sort of play around with it. But what it means is in the future, as we can add more tasks, if what you're interested in thermal performance, you can drag the combined performance score to prioritize thermal performance. If you're interested in XYZ, hopefully you'll be able to say the best model for my purpose is this. So this is a sort of a completely open science project. Everything we do is discussed in GitHub issues. If you have any task that you think is relevant at a PBE level, because all the models are trained on PBE data, please contact us. We will add it. We will credit you. We will put it on the website. We will make sure that you get the exposure that it should have. And so now, sort of talking about this, I'm going to talk about a model that we have built internally at Radical to address sort of some of the concerns we were having with the models that were available. So one of the things that is really important for us if we want to scale is sort of scalability. And I'm running out of time, so I'll go a bit faster. So we took this GemNet OC background, and we saw that, which can fit very, very well, but it's actually, as you scale it, is quite memory intensive. So we said, if we pre-train it on this sort of quadruplet task and then move to the triplet task, sort of canceling out this quadruplet interaction block, then what we can actually do is we can dramatically reduce the inference time and memory use with minimal impact on the errors. The other thing that is sort of important about this Egypt model is that by sort of carefully studying things like the neighbor list, you can see on this targets application, it is the only model that is achieving both sort of good performance at this kappa-SRME task whilst not being gradient-based. And what this actually shows is that what the gradient-based models are giving us is like a smooth potential energy surface such that we do well at this, these phonon tasks. But knowing that we want a smooth potential energy surface, we can tune our decisions in training the model to achieve a smooth potential energy surface. So the ways that we can do this is sort of this classical, if you're a comp chemist, you know that you should always run things in double precision. Running things in double precision helps a lot. And the neighbor list is actually a critically important part of these models at scale. Lots and lots of pathologies in using MLIP models will come from incorrect neighbor list constructions. So if we make the displacement slightly larger and have a sort of an extensive neighbor list, then we actually see that the PES becomes very smooth and we start to get good performance. The final thing I want to touch on in the last sort of 5 to 10 minutes is TorchSim. So when we got this sort of 1000x speed up moving from DFT to MLIPs, lots of the MLIPs have standardized around sort of ASE as an interface to allow them to be sort of readily usable by many people. And the problem we were encountering with ASE is when we started to run our workflows with ASE, we're actually running quite small, sort of what's called special quasi-random structures. And so we're only ever using sort of 1 to 2% of our GPU memory. So we've got this 1000x speed up, we can maybe just be happy with that and take it to the bank, but then we're sort of dramatically underutilizing our hardware. And sort of one of the things about Newton's equations is they're sort of, because they're embarrassingly parallel, you're working on local environments, these things are inherently batchable in the way that GPUs accelerate computation. And so we've written our own sort of MD engine to batch these simulations more effectively to use our GPU memory. Thank you. So sort of go back to these graphics, sort of DFT is sort of 1,000 times slower, we get our 1,000 times increase, and then as we efficiently batch these things on the GPU, then we sort of can get sort of further multiples. And what this actually opens up for us is quite interesting. So one of the sort of major challenges with comparing these MLIP models is that speed comparisons are incredibly difficult. So here you can see that our Egypt model at the smaller system sizes is the sort of fastest in a serial performance manner. As we scale to larger system sizes, different systems perform better. And so anybody who presents at the moment a speed comparison between models has made implicit choices that will affect which model is ranked best. And so, but this is due to things like batching, due to neighbor list constructions, whereas if we used our batch primitives in TorchSim, we see that as we scale the system size now, we have a much, much more consistent ranking of the models in terms of speed, which sort of is steps towards having what might be deemed a fair speed comparison for these tasks. So here are some sort of early results on the sort of speed up acceleration that we can get with TorchSim versus ASE for the various tasks that we're interested in. So you can see that for these sort of small systems, so 32 atom sort of quasi-random cells, we can get sort of dramatic speed ups of up to like 50 to 100 times when using MACE. So sort of TorchSim is powered by these two sort of high-level auto-batching primitives that were designed by my colleague. So there's spinning auto-batcher, which is upfront, if you know the calculations you want to run, then you can sort of allocate them such that you're fully using the GPU memory, which leads to high utilization. And then in tasks like structure relaxation, where you don't know a priori what you want to run, we also have this in-flight auto-batching optimizer that will sort of consider, will sort of take in and out of the queue calculations depending on whether you've satisfied some convergence criteria. So these are sort of the two primitives around which TorchSim is built. We have decided to open source TorchSim because we believe that sort of these tools are able to be used sort of quite universally in lots of applications, and it will benefit both us and the wider community to have sort of open source development in a similar manner to ASE, and we're already seeing some contributions of things like nudged elastic band and correlations. So with that, I'd like to thank the team. The TorchSim work was led by Abhijit Gangan and Orion. Here's me and Janosch, who did the map bench discovery work. The DFT is mainly being done by Yuri Sanspur. and Stefano Folletta. These are our co-founders. Adish is responsible for the Egypt model, and then everybody else is the wider Radical team. Thank you very much.
Thanks a lot, Rhys, for this super nice talk about also benchmarking. Do we have questions? We can start with Andre.
Thank you for. Thank you for a very nice talk. I have a question about the very last part. How about Torchsyn and AMD GPUs? Are they compatible or not?
We haven't studied it. To the extent that PyTorch is compatible with AMD GPUs through ROCm, it should work, but there are sort of lots of system limitations there.
Thank you.
Yep, let's go there, and then we go back.
Yeah, thank you for the very, very interesting talk. I have a question about comparing models in terms of number of parameters that they have. So what is your opinion? Like, because some models have a lot of parameters per data, and some others are less, kind of having much less parameters. What is your opinion on how stable they would be and how it relates to, let's say, performance, or how well they preserve symmetry and so on?
So in general, the trend in the ML space is that more parameters gives you a more flexible model that allows you to fit more complex data sets. And so over time, here on this plot, you can see that the early models are sort of vanishingly small points. I think we're scaling with parameter count. Yeah, and later we have seen much, much bigger models. In general, there isn't a great correlation between number of parameters and performance. There isn't even a great correlation between the number of parameters and speed, which was one of our early reasonings for trying to record the number of parameters. Because what actually matters a lot for speed is the sort of internals of the mathematics. So sort of in these equivariant architectures, you can have a lot of parameters that aren't used. You can have slower operations, whereas in some of these models like ORB, which are designed to sort of mimic transformers, they have much, much more efficient matmul applications. And so they can have larger numbers of parameters without sort of reducing the speed. So in some sense, the number of parameters, provided it is sufficiently large, isn't really a source of signal. If you have too few parameters, you will not have sufficient complexity to fit your data. But having more parameters, in my opinion, isn't necessarily better.
Sorry. Nice talk, thank you. My question is mostly related to the phonon lattice thermal conductivity. So I would imagine that the data used for the training is mostly from calculations, not a lot from experimental data?
None of the benchmarking results presented are experimental.
Yeah. And it will be mostly for the high entropy alloys, probably.
So these results are actually presented on 103 sort of crystals were picked by the collaborators. None of the benchmarking results are on our internal data sets. These are all things that are already public.
Yeah. No, my only question is because sometimes there are some problems with the calculations related to layered materials, in which the lattice thermal conductivity, you have different values in the in-plane and then in the layered direction. And several calculations that exist kind of do an isotropic lattice thermal conductivity, which should be carefully sometimes taken care of. And I've seen papers that do not consider just doing the
anisotropic effect.
Yes, exactly. Because in layered materials, this is very important, especially when you look at the kappa in the out of plane, because these values influence, of course, then you get different values for the CPIC coefficients as well.
I would have to say that I do not know the sort of which materials were picked sufficiently to say whether or not any of them are layered structures. I think because these calculations are very expensive, the data set is very small, and I think the structures that are picked are sort of quite small conventional cells. I know that the Professor Simoncelli's team are working on trying to expand this data set because already we are seeing that this sort of kappa-SM task, which initially was really great for differentiating models, is already beginning to saturate.
Is there some super urgent quick question? Okay, but that's the last.
I know we're short on time, so just really quickly, first part of your talk was, hey, we're building this awesome autonomous system.
Yeah.
Second part was, we have these great computation. Can you talk a little bit how you're going to integrate the two? What is it that you're going to feed out into the model that's coming from DFT that you think is the most important?
So one of the ways that we're thinking of integrating the two is in the sort of Bayesian optimization design of experiments paradigm, you can have continuous optimizations or you can have pool-based optimizations. So a sort of the most obvious bridge between the two is that we run some sort of loose conventional screening campaign computationally. We have a subset of 100,000 multiple principal component element alloys that we might want to study, and then we use a sort of Bayesian optimization framework there. So that's not integrating the experimental data back up to simulation, because I think this is exceptionally challenging because of the data scales involved. So sort of on our MLIT level data scale, we have sort of hundreds of millions of data points being produced by sort of groups at Meta, Professor Botti's group and her collaborators. These are sort of, if we have 10 experiments a day, we will not be able to retrain our MLIP model in a way that actually affects its performance. So the sort of bridging of things is, can we narrow down the space computationally? Can we produce a candidate pool computationally? And then we'll be applying sort of more conventional sort of design experiments on Bayesian optimization work to steer the lab day to day.
Okay, then let's thank Rhys again and move on. And our next speaker is Andre from the University of Turku.